a smoking gun, really. So we did this experiment where we just had no radioactive source, and then we bring the source in, and bring it out, and bring it in, and then we would look at what when we reconstructed candidates events, and you can see that they're extremely correlated with the radioactive source being present. So we kind of had no doubt that we had sensitivity to these particles at that point. It was really exciting. And so we started looking at some of the shapes, and so this is just to give you an idea of what this looks like. So your camera, right, is going to make, this is essentially the data that would go into making a picture, and the size of these blocks is how much light the camera is recording. And so these events cause what look to us as particle physics, these look very much like sort of calorimeter events, or little clusters of energy that tell us that a particle passed through. And then in some cases, we have charged particles like muons or protons, which are beautiful straight tracks. So this was a particle like a muon or a proton that passed right through the CMOS detector in the camera, leaving a nice straight track at a very glancing angle. So we get some beautiful events like this. So, you know, we wanted to understand better what the performance of these phones were. So we did some things like expose the cameras to muon beams at the CERN experiment. And so the idea was, you know, we just put a phone here, lying flat, so we get these sort of, so the tracks would really pass straight through it, or as close to it as possible. And we just put this in a muon beam at CERN, and you can see you got these nice muon tracks passing through the camera. So it's quite a lot of fun. And now here at Davis, we're also trying to use the fact that we always have these cosmic ray muons. So what we're trying to do is set up a test stand, which you see here, and what it essentially is a conventional detector that can spot a muon that we're used to, and then we compare, you know, when it passes through both of these, we know it was likely to pass through the phone camera, and we can check if we saw an event in the phone as well. So, okay, so then we also do some other experiments, like we have friends that work in these experiments that are deep underground, so they're running our application down there, and here at Davis and Irvine and other places, we're already running the app on the surface, and whenever any of us go on a plane, we run our, now that it's allowed, we run our phone in the airplane mode, and collect data when we're up high. And the point is, cosmic rays have a very high rate up where a plane flies, high in the air. It's lower rate at the surface, and the ground, which absorbs a lot of these cosmic rays, results in a very quiet environment in the mines. So we can look at the rate differences, and from that understand how the phones are working as well. So we put this all together by simulating how these events look. So this is a computer simulation of what these showers look like. So we do all that at this point, all with the simulation, and so we can sort of predict how these events will look to us. So our idea is that we have lots of people running our app, and the data will be collected on a central server that we already have running. And what we'll see, so the data that we'll collect is which phones were on at certain times, and whether or not they saw a candidate. So those are the red dots that are hits here. And so it turns out that, you know, if you have a higher energy shower, you have more particles, and so you'll get more hits. So essentially, what we have to do is look for a large number of hits in a small area, and then we know one of these high energy showers occurred there. Now we actually do that using some pretty sophisticated analysis that even takes into account the fact that the shape can change based on the direction of the shower. So that's how we reconstruct these particles. And then what I'm showing you here is just our estimate for how well we can measure the energy. So if we're down here, that means that we sort of have a 10% what we would call resolution. It's like how precise our measurement would be, 10% of what we measure. And so these are all different scenarios that are more or less pessimistic, and so we can see how our performance behaves. So what that turns into is we can go back to that fact that we're looking for these very, very rare particles. So this is a rate here. This is how often these are happening, and so that's this line here. Now these different colored bands are, with our network of smartphones, how many events, what rate we expect to reconstruct them. And you can see that for low energy, there just aren't enough particles to really trigger our smartphones. But because at higher energy, there are many more of these particles, our phones start to do a lot better in all of the different scenarios. So what we think we're going to be able to do is really fill in that high energy picture for these extremely rare events. Where even though we have the phones themselves are not great detectors, they weren't designed to be detect these, but there are so many of them, and they cover the entire world that at a certain point we think we'll be able to compete. A real challenge for us is controlling noise, though, in all of this, right? So whenever you're trying to make a measurement, you want to watch out for noise as well. And so this is a little picture of what our data looks like. So each phone, say, has a point here, right, along the bottom. And as you move in time, what's happening is each phone, so these are little hits from noise, where the phone just happened to think something happened even though nothing happened. So that's a source of noise, right? And so what a real shower looks like is a bunch of hits on phones that are all simultaneous in time. So that's a real shower. Now, if we can do a very good job of putting the times together, then we can tell the difference between a real shower like this and when you just have sort of a random mix of events from noise, right? But if our timing resolution is really bad and we can only distinguish like this, then what we have is, here we have, 7 events, right? 7 hits. It looks to us like a real shower, just like this one. So for us, the timing resolution is really important. So we do other experiments where we fire a light-emitting diode and see how well the phones can time in on it. So that ends up being a really important part to us. But one cool trick we can use is we can actually, from the data that we collect, we can easily figure out what the random noise is. Remember, the real showers look like this. They're all coincident in time. So all we have to do is take the data that we've collected and scramble it up in time. And just shift each phone by a random amount like this. Here we go. Right, just scramble it up, and we can sort of make our own prediction of what our noise should look like. So that's quite useful. Okay, so the app itself has come a long way since our first version. So you can see that my friend Daniel has a sense of humor with this advice, Irvine Davis. So anyway, here's our application. And I think what it does is it's designed to be very non-intrusive for the user. So it only launches automatically at night when your cell phone is charging, so it doesn't waste any of your battery. And our idea is that people will just download our app, and then when they charge their phone at night, it's the ideal conditions for us. We need sort of dark conditions. The app will just, when it detects that it's not being used and it's being charged, it will automatically launch. It doesn't use any cellular data or any of your, it only will upload data to our server over the home Wi-Fi. So it's designed to be really quite unobtrusive. And it just sits there waiting for these cosmic ray events, and when it sees one, it uploads it to our server. So that's the idea. And now I have, how are we doing out of time? I would like to do a little demo here. Oh, so we're good, right? Good. So let's just switch over to. So hopefully you can see that. So what in this mode, what we're doing is looking for candidate events, and rather than wait around for a cosmic ray event, what I have here is a very weak radioactive source, and I'm just going to put it right on the camera here, and let's see what happens. No. We're taking it. I'm on the wrong screen. There we go. Okay, so what you see are raindrops for each candidate that the phone reconstructs. It tells you the position of the reconstructed candidate. And so if I take the source away, that's what's going on. That's why it looks fine to me. No, there it is. So now let's put it back on. There we go. The raindrops return. There we go. So what you're seeing here, actually, interestingly, also is the particle nature of light. And this is kind of cool that with smartphones we can see. I mean, you would never think this is a wave, right? You're seeing the individual points from individual particles of light right here. So that's essentially what we do. So let's go back to the top here. I had a backup demo which we can skip now. So yeah, if you're interested in volunteering your smartphone, you can join us here at our website. You can also just Google crayfish without the H. People, kind of snarky reporters, teased us that we didn't think. So crayfish stands for cosmic rays found in smartphones, and some people wrote that we should have added an handheld so that we could have the crayfish. But it turns out to be extremely convenient to be crayfish without the H. If you Google us by that, you'll find we're the first hit. So that works out quite well. So go ahead and if you're interested, join us here. You can read more about the project, and you can sign on to be one of our beta testers to run your app on your phone. So to give sort of a sense of the timeline, we had our first paper that looked into the feasibility of this back in October, and just a few days later we had quite a bunch of press coverage, and we had 25,000 users sign up. And since then we've had a few waves of publicity, and so now we're up to about 100,000 users signed up. Now we can't quite, we're still beta testing our app, so we don't want 100,000 bug reports for every mistake that we make in our code. So we've sort of been throttling how many people we sign up. So for now, we're just keeping a list, and then we have a few thousand people that are running our application right now. But our hope is that we'll be ready by early summer to go into open beta testing, where we just allow anyone that's interested, and any of these 100,000 people so far that have signed up to run our application. So also the collaboration, which started out as a fun little project from Daniel and I, has now grown. We've gotten some much needed help from other institutions, and we even have some partners in industry. Most recently, Amazon has very graciously generated us the server time that we need on their platforms. So that's been extremely helpful for allowing us to scale up. So here's our paper, if you want to read it. We've also had really, which is important for our project, which is really based on citizen science, we've had a lot of press coverage. So here's where we went into our initial data testing. Actually, I don't know why I had to fake that we have news coverage, because we actually do have quite a good press coverage, so I just couldn't resist that joke, I guess. So we were covered in the New Yorker, which was a lot of fun, and that's a magazine I really like to read, so it's incredible to be featured in it. And then more recently on NPR, we had a little radio spot. So we've gotten some pretty good coverage, and that's really helped us attract users. Before we go about questions, I just wanted to give sort of a little one last sort of my big perspective on the project. And it comes down to these experiences I had. For a few years ago, I was like late at night, and I was returning to my apartment in Chicago, which was built hundreds of years ago, and the fuse box is down in the basement, and the power had gone out. have a flashlight in the house, and I was thinking, it's 2 in the morning, I have to go out to the hardware store and buy batteries or something, to get down there. And it suddenly occurred to me, no, I can download an app for that, right? I just downloaded an app from my smartphone, I head down and I change the fuse out, and I got to go to sleep, right? So that was, and I thought, okay, this is like kind of a one-off sort of thing. That's pretty cool, but it's not going to happen again. And more recently, I had finished the solutions to a final exam, and I was thinking, I'm going to drive into the department and scan these so that I can upload them to the students, And then I found, no, I don't need a scanner. There's an app for that, I can download this little tiny scan app, take a photo, and that replaces the scanner, right? And so, I don't know, crayfish, it's a stretch that we're having a lot of fun with it. It's the most fun project I've worked on, but the science, getting science out of this is going to be a real challenge. We have some real hurdles ahead of us. But I think that the general idea that we're going to be increasing these sophisticated personal devices in order to do real cutting-edge physics, I think that idea isn't going to go away. And sure enough, I just wanted to give another example of where we're crowdsourcing, not just the computing, which has been done before with like the SETI experiment and so on. This is crowdsourcing the actual detection, and here's another project that's attempting to use smartphones in order to map out, get a very accurate map of the Earth's magnetic field. So that's one of the things I also find exciting about this project is that I think we're really looking at a new way to do science. That's frankly a lot of fun. So that's all I have, but I'm happy to take questions. Yes. Yeah, that's really the particle nature of light that you see there. It's just if it were really like a wave, like light were like a wave approaching a beach, right? It would affect the whole beach. You get a little disturbance that's spread out over the entire beach, right? But these particles are very high energy. These light particles are really particles, so all of that energy gets concentrated in one particular spot. And so it ends up knocking off one particular electron that ends up in one pixel of the smartphone, or just a few of them nearby. And so what you were seeing is the random position of those hits in the smartphone camera. So that's what's going on there. More questions?
Okay, in the test idea, I noticed that you put a specific light source that is very close to the detector.
Yes.
But normally the typical detector activates or produces electrons given some range in the source. Which means in this case we are trying to measure cosmic rays, and I'm trying to understand the difference between that experiment that you have put there with a specific test source on top.
Right.
That can make some energy just kind of adapted to that sensor, and a real cosmic ray source that can, what is the
Exactly. Yeah. But we have a very, by now we have a very good understanding of these different processes, so we can scale them up. So essentially, when we put the source there, it's just like a much faster. It's just many more events. But we understand that there were more. So we want to measure the efficiency essentially. We want to know if there were 100 chances to measure something, did you see something 1 of the times, 10 of the times, or 100 of the times, right? That's what we're interested in. So we know when we use those sources, how many possible events there were, and then we just have to compare that to how many we saw. And then we can scale that to the much more rare processes of cosmic rays.
My question is that sort. How close is that sort to the real sort that you want to measure?
Yeah. There's a whole mixture of particles in these showers. What we think we're most sensitive to are actually the muons. And that's why for our purposes, what's sort of most important are those tests I showed where we see the muon tracks, and those experiments where we look at the different rate between what we see when we run around in a plane versus versus